So one of the things I picked up at the Mike and Key Hamfest and Swap Meet was this little power supply. And, I've got a couple of Rigol bench supplies here. I've got a DP811 and a DP832, and they're really nice supplies. Normally I wouldn't pick something like this up just because I've got a couple really nice bench supplies. But what intrigued me when I looked at it was on the back of the supply, there's sense pins. And I'll talk about what sense pins do. So typically when you got your power supply hooked up and you've got your leads coming out to whatever you're going to power, there's voltage drop in those leads. And as you push more and more current through, the small resistance of the leads and the connections can occur more and more voltage drop. So I might be outputting 6 volts here, say 2 amps, and I've got a foot and a half of lead length coming over to my device under test, and the voltage over on the device under test might be at 4.95 volts or 4.9 volts, depending on the voltage drop. In the current flow model, we've got current flowing from the negative. Kind of get my hands in here. I've got current flowing from the negative around to my load, and then through the load, and then back up to the positive pin. I'm talking electron flow here. And so that wire length, there can be a voltage drop, and most of the time you just don't care about it. If you're powering TTL logic and there's a bit of voltage drop, you don't care. But sometimes you really want the 6 volts that you want to drive very accurately at the device under test. And what sense does is you bring 2 more leads back that are attached as close to the load as you can get them. When you bring those leads back to the sense pins here, you remove these little jumpers to the sense pins, and that's a very low current path. There's almost no current in that sense circuit. And so what happens is the power supply will sense out here at the load that it's only, say, 5.95 volts. And so it'll drive the output up by, in this case, 0.05 volts to get exactly 6 volts out here on the device under test. And so what you could end up with at 6 volts is, say, say we've got really high loss in the cables. You might be driving 6.1 here. On the terminals, you've got you've got 0.05 volt drop on this lead coming down to the device under test and 0.05 coming up. And so it's going to drive this to 6.1 volts. You minus the 0.5 on the 2 sides, you end up with 6 volts exactly, across the device under test. So that made this kind of an intriguing little power supply. It's got a pretty large transformer here. I'm sure it's a linear regulating power supply. There's just not enough stuff in there to be, I don't think, a switcher, especially with a transformer that size. There seems to be, well, it's hard to say, getting shouting down there, but that kind of caught my eye, and I went, that's kind of cool. It could be a very useful addition to my stack of power supplies over there. I don't know the actual rating on it, but the voltage output goes up to 20 volts, and the ammeter goes to 1.2 amps. So that's going to be 20 some odd watts, which is respectable. Again, kind of an indication of quality here on the voltage control is there's a gross potentiometer here, and there's a fine adjustment here. And again, they're both just single, turn pots. But again, gross and then very fine control. It is current limited. It feels to me like the knob is just spinning on the shaft of the pot that's meant to drive. I don't think there's like a 10-turn pot back there. So that's something we'll look at. It's manufactured by PowerMate Corporation, PMC, from Hackensack, New Jersey, made in the USA. Underneath there is a part number BPA20C, 105 to 125 volt input, 47 to 63 hertz. It's very nice here for the US, kind of across the entire country, where there's slightly different voltages depending on where you are in the grid. There's nothing here that really gives me, well, there is right there, 47th week of 1990. So that would be the manufacturing timestamp or date stamp, almost guaranteed. 47th week of 1990. So it's nearly 20 years old. That would tend to say the electrolytics in it are well beyond their service life, but I went, what the heck? I can actually vibrate it, see a large filter capacitor just, yeah, there's a large filter capacitor right down there, an electrolytic. It looks like that it's just loose. It's just, as Dave Jones would say, flapping around in the breeze. When I get the cover off, I'll show you what I mean. So kind of the first thing here, I'm not even going to power it up. I'm just going to go ahead and open it up, and we'll do a visual inspection. We'll see if we can repair whatever damage there is. And see if we can bring this guy back to a serviceable state. You know, it's one of those projects where I really don't need it. My DP811 Rigol power supply actually has sense pins built into it as well, so I can do a 4-lead, you know, power drive from it, and you know, it makes it a nice supply. It's only a single output supply, whereas my DP832 has 2 adjustable and 1 5-volt fixed, and 2 of the adjustable can be set up in a positive negative configuration, where the negative of one supply jumpers the positive of the other, and that way you can generate, you know, a rail above and below the 0-volt reference, which is often very useful. You know, if I'm working around op amps or things like that, you need a, you know, a differential around ground voltage. But you know, this guy just kind of caught my eye. He was cheap. He's in decent shape. Let's see if I can get the top off here. There's a nice large electrolytic here that's just flapping around. It is connected. It looks like there's a really loose wire strap here to just kind of keep it in place. This looks to me like somebody at some point, no, he is disconnected. So hopefully this is showing up in camera. Take a peek at the screen here and see. Let me lift this up a bit, get you a little bit better view. So on this electrolytic, you can see this lead here has broken off, and this capacitor is just flapping around, and I'm sure that's why that lead, through mechanical stress of movement, is broken off. I'm guessing this isn't really the original cap, and when I look at how the wire strap is done in there, that's further evidence to me that this capacitor was replaced by somebody at some point and not done very well. If we lift him up out of there, again, you can see the broken lead. Yeah, there's a really ugly patch here with shrink tubing. You can see that this tie strap is just under a couple of power resistors here. You know, if that's meant to dissipate 10 watts there, I think those are 5-watt resistors, or maybe they're 1 watt. That's just not a good idea. You're restricting the airflow around them. Just whoever did that repair didn't do a good job. So the question kind of becomes, there's a red lead running up under the board there. That seems to be potentially the other side of that broken wire down in that hole. So of course that's repairable. I would just replace this cap. You know, it's 5,000 microfarad, 50 working volts. So it's rated well for this. You know, the power supply goes to 20. I think it was 20 volts. So I'd expect there to be probably 25 volts across this cap to give it some margin above the output. Might even go as high as 30. So that's kind of an interesting, poorly executed fix somebody did at some point. There's 3 large pass transistors in here. This is where the voltage regulation is going to happen. It's through those 3 transistors, and I'm just assuming they're probably paralleled. It'll be interesting to see if that's correct. Let's see if we can figure out what they are. They are date code, well, 20th week of, let's see, no, that can't be a date code. Well, it's time for a glasses shuffle to see if I can actually read the numbers on those. I'm assuming the 274 is probably the part number. These might actually be, they have a PMC stamp on them, and PMC is the manufacturer of the supply. I wonder if that's a house part number. And I look further now, I'm sure that 7845 is a date code. There's a 79, or maybe that's an 8. Yeah, they're all three 7845. If that's really the manufacturing, a date code on them from 1978, when we think the supply was probably manufactured in 1990, it would have meant these caps were 12, or these transistors were 12 years old when they put them into service. I'm a little doubtful of that, but it could be. You know, it's dirty inside, but the build quality seems okay. So there's an LM723, 2 of them. I believe those are op amps, if I remember correctly. So that makes sense. Just the regulation circuit here. So there's a trimmer pot here for current minimum, it's labeled iMin, and a 10-turn pot here for what's labeled iMax. It looks like this pot here is voltage output max, MCAL-V. So I'm assuming these two here are some kind of calibration. I've not looked for a manual for this. It's pretty standard kind of build in my mind for the, thinking about into the 90s. This does look more to me like I got 80s or maybe even back into the 70s. It's a single-sided board. It's not fiberglass, I don't think. It might be fiberglass looking at it, but it's a single-sided board. The ICs are socketed. That's nice. The more I look down in there, that is the spot where that filter cap has come loose. I can see tearing this down is not going to be a joy. Looking at the binding posts, based on the color, I'd say those are beryllium copper, which is, you know, a higher quality binding post. It's just not a cheap tin metal of some kind. You can see here the 2 potentiometers. So there's the gross voltage adjust that we talked about and the fine voltage adjust. And I can see turning the fine voltage adjust, the shaft turning back here. So I suspect this back pot is fine. Voltage adjust on the front pot is the gross. I can tell just by the feel that these appear to be wire round potentiometers. And by the sound, I'm sure you can't hear it, but there's a different sound when they're wire round because the wires aren't perfectly smooth, and so it makes a little bit of noise. So the wire round tends to indicate a little higher quality pot. Looking at the current limiting pot, that just looks like a normal. Oh, that's quite interesting. That knob is not loose, and I've never seen a potentiometer like this before. How do I get this on camera? I don't know if you can, I don't know if I can get you a view down in there or not. Let me stand up where I can see what we've got on camera somewhat. There's 3 large ball bearings on the back side of that potentiometer, and as I turn the knob, you can see them slowly rotating. And it just hit a bottom on one side. Now if I turn, again you can see those ball bearings rotating if I can keep it in shot here. And it's still moving, and there it hit the other side. So although it's a single wipe, you know, there's a single wipe around potentiometer, what's happening to me is it looks like the shaft off the knob comes up through the center of the 3 ball bearings. I've got this off camera again, apologies, it's hard to see. It's like the shaft to me of the knob comes up between the 3 ball bearings, and when you turn it, rotates the ball bearings, and so it produces a large reduction set. You know, that small shaft is taking lots of turns to rotate those ball bearings through one true rotation, so it's really a big mechanical divide by to give you real high precision on the current limit. I've never seen a potentiometer like that before. With ball bearings like that, that's really fascinating. And something brand new. So, where to kind of move next on this? It's the ground side of the filter cap that's broke off here. And I'm going to guess, we'll find out here, let me bring up the meter. I'm going to guess that probably comes around to the chassis ground. Although it may be isolated from chassis, it's hard to say. But I'm going to guess either it comes back to the chassis. We know it's going to go to the negative binding post here. Let me get the meter in continuity mode. So I'm going to get down here on the black binding post, and we have continuity there as expected. Do we have continuity to the metal chassis? No, we don't. So it is isolated from the chassis. Okay, no surprise actually. But what this does mean is I could temporarily take this filter cap and jump it over here onto the negative binding post and apply a bit of power and just see if there's any life at all in the thing. It's just kind of a matter of figuring out how to do that safely. Might be able to catch it like that. Do I have a piece of something I can insulate with floating around here? And we'll just do a really gross, cheap temporary fix so we can apply power to it in the video and just see if it'll come to life. Maybe the easiest way to do this is just to use a clip lead, as much as I hate doing that. This is of course going to be far from an optimal fix. Looks like we'll come in this way, just to insulate a bit better. I do want to make sure that I do get continuity. A couple of these cheap alligator clip leads I've got are open, but that seems to have good continuity. The power switch is off. Those are nice and squeaky. Get the meter in volts. We'll just do a temporary connection here, just enough to hold the meter leads in without actually bending them. So we've got a temporary fix in for this filter cap. Set the meter to volts. I've got the voltage cranked all the way down. I'm assuming that rotation that way is the current limit all the way down. You know, mechanically, the rest of it, kind of in my first visual inspection here, looks like it's safe to power up. There is a filter cap directly on these back outputs down there to come through to the sense. He is isolated, so we're either going to get smoke and fire here, or maybe it'll attempt to power up. Let's see what we get. Well, no smoke and fire. I'll try bringing the voltage up here. And that should be about 5 volts on the meter, and I'm reading 5.35 volts up on my voltmeter. So from a quick check, looking for stability here. So it's measuring 9.000, 8.997, 8.996, 0.997. It's stabilizing. Over time here, it's getting more and more stable. This is now stable out at 0.0054 volts, 0.0053, 0.0052. It's coming down slightly. This is really becoming stable out to 4 decimal places, which is, there's no load on it, so that's kind of nice. See if I can tweak the voltage directly to 9 volts. Still pretty touchy. I bet the potentiometers could use a good cleaning. Apologies that you can't see the meter here. It's a bench meter. It'd be almost impossible to get in the shot. But I'm set to 9.0070 volts, and it's still moving up and still moving around about 0.0005 volts, maybe a little more than that. I'm sure this capacitor isn't particularly happy. Wonder what the gross DC voltage across that cap is, just out of curiosity. We can go ahead and measure that. See if my prediction was anywhere close. That should be in shot. Get onto the negative lead here. See if I can get a connection down here on the positive without blocking the meter. Oh, 34, so it's definitely 5 volts or so higher than my top guess. I think I guessed 25, maybe 30. So there's 34.5 volts across the filter cap. It's a 50 volt rated cap. It's well within its spec. That gives the power supply lots of margin above the 20 volt max output. So if there's large shifts in the current demand, the voltage across this cap is going to dip during that large current demand. It'll may recover once that current demand becomes stable, but it gives it lots of room so that we're not ending up dipping under the voltage output we're asking for. I'm going to bring the voltage output up to the max, and the max is about 20.85 volts. Which is no surprise. It's rated up to 20 volts according to the meter. See if I can get it pretty close to 20. Of course, there's no load here, so I would expect not to see much ripple current. I'd have to break the scope out to take a look. Anyhow, it looks like it's a pretty decent little power supply for what it is. It's really holding with no load the output voltage, really steady out to 3 decimal places. So now the question becomes, should I put some load on it? Part of me is thinking, why not? We're already kind of abusing it, so I don't know if I can get this lead clip down on there, just so we can monitor. There it is, so we can monitor the gross, the gross DC voltage on that filter cap. So of course we've got our step-down transformer going to a diode bridge that I haven't spotted yet. There's going to be a diode bridge someplace here. That's interesting. I'm not seeing the bridge. To the cap. Let me tilt it up and see if I can spot. diode bridge someplace. I'm really not seeing. That's really interesting. I wonder if these have got to be. I wonder if a couple of these are being used as diodes in some way. That's just kind of odd. Where's the regulation taking place at? And it's got to be. But the large heatsink, you know, 20 volts going to 1.2 amps is, you know, over 20 watts. It's significant, but not huge. Yeah, that's really curious. Where is the diode bridge? I can feel the case humming a little bit with the power transformer. You know, it might be mounted up under the PCB, perhaps, using the chassis as a heatsink. Let's try to safely move this back a bit. And let's put some loads on it. This is a little block of 470 ohm resistors. There's 10 of them in parallel, giving me a 47 ohm power block. It's kind of meant as a gross 50 ohm high current terminator. It's kind of what it was built for originally. Not the best build I ever did, but at the time I put it together, it really served the need I had. So let's put some load on it and see what we get. I'm going to crank it down to about 10 volts. See if I can get again these cheap Chinese alligator clips to do something. And they are cheap. I got a bunch of them cheap, and as I keep saying, they are cheap. Got to pull the boot back on this bit. Let me see if I can get this pretty close to 10 volts. There's 10.002. I'll switch the little meter over to amps. This isn't going to be a huge current draw. Am I not connected someplace? 10 volts, 50 ohms. You know, 5 ohms, it'd be 2 amps, so this should be, what, 200 milliamps? The meter hasn't even moved, so there's something not right here. Did we have a failure someplace? Oh, wait, I bet we hit the current limit. Maybe. I don't understand, though, why I'm not measuring anything on the filter cap. Oh, and that's because the ground lead has come off here. Okay, we've got our 34 volts across. We are seeing some loading effect. So there's 34 volts, 34.6 across the filter cap, and if I load it, it does drop to 33. So we are seeing some loading effect. Finally the meter movement is moving. So according to the meter movement, if I can read it, 0.6, 0.3, yeah, 200 milliamps. So yeah, the meter movement's right on 200 milliamps, which makes sense. You know, the 10 volts divided by about 50 ohms, so 50 into 10 is going to give me about 0.2 or 200 milliamps. That's geese outside. And that's really the most I'm going to be able to draw with this load. I actually need a load that can draw some more current. And I've got a couple here. But this is a good sign. Like I say, the meter movement is operating. I'm bringing the current clamp back down, and I have not seen it go into compliance. There it goes. So it just dropped into compliance. The current just rolled off. It could supply. You see the the filter cap voltage come back up to 34. You can hear the output meter. So in full compliance, it's dropped down to 0.2 volts, 59 millivolts. So it shut the output off because it's drawing more current than I have it adjusted. The compliance on it. We're back up at the 10 volt output. It is stable to 3 decimal places. Quick and dirty look. It's actually not too bad, a little power supply for what it is. Some repair work, some cleanup. And this might be a nice addition on my bench here. It's relatively small. It's only a single output. So why we ended up measuring, it's up to 10 volts. Yeah, there's maybe a defective switch. I can't get the meter to measure current again. It's just sitting at 0 in the current setting. That may be just an issue with the switch. There it is. So there's an issue with the mechanical switch to get into current mode. And that's actually up around, that's 300, that's 150. Yeah, again, it's right up around 200 milliamps a draw. Well, that's interesting. I guess the next step might be to actually get a larger load on it and see what we get. So I guess we can do that here. Turn it off. I'm going to remove this load. Of course, this didn't even start to begin to warm up. 200 milliamps across. That kind of capacity is rather large. Let me move this all back out of the way. Hopefully you can see the filter cap rolling off here. The voltage on it as it slowly drains down. Let me grab an electronic load. You may recognize this load from the first, video I ever did on the channel. This was it Fred Fish? Was that the company? Where's the electronic load? 5Fish, 5fishaudio.com. So this is an electronic load. It's got a couple of MOSFETs up underneath these large computer heat sinks with fans. It's using those 2 MOSFETs in parallel as a load. It's got a decent adjustment range here. I was never happy with this potentiometer. It's something I've been going to replace. This is a cheap Chinese 10 turn. And it's just not a great potentiometer. But what we're going to do here, grab that's current sense. We'll just go ahead and screw these binding posts back on. And the problem with the small bench here is getting everything kind of in shot. Oh, I'm dragging the screws all over with cables. See how much of this I can get into shot. I need to get the power lead for the electronic load brought around where I can connect it. So I've got power to the load. How much of this is in shot? The meter obviously isn't. So that's That's looking at the voltage across the filter cap. Again, this is very how you doing with the way I've got this all hooked up. This is the load side. That's negative. Load side. Positive. Again, these aren't going to be real high current capacity. Apologies for the fan noise, but bringing the unit up does. Bring the fans up. I've got two independent DC power supplies in the box, one to run the fans and one to run the electronics on the board, and that was just the best way I could find to isolate the noise these fans make from the unit to get a little more stable. Okay, Mr. Meter, I know you want to time out. So I'm going to go ahead and turn the load on. I'll bring the power supply back up. The current's dancing around. That's maybe the switch not making good contact. So I've got a small amount of range here to play with the current draw. I can't tell if that's the meter movement having issues because of the switch here. You can't see it, but the needle on the meter is dancing around. I'm trying to remember. Digital voltmeter, yeah, 1 millivolt equals 1 milliamp. So let's see if we can get. This guy got good batteries in him. Let's see if we can get some leads set up here to try to measure current. Getting lots of leads here in the setup. That's common. Volts, ohms. Who's beeping? Is this low battery? Are you beeping because you think I've done something wrong? It's unhappy with something I've done here. Lead combination volts and ohms, common. Microamps, milliamps. I'd swear that's the correct. Okay, I have no idea why that's unhappy. No idea. Let's take him to 40 volts. We're going to do a little bit of ugliness here. I'm going to turn this guy into the voltage monitor for the gross filter cap voltage. This meter's really unhappy. What's going on here? DC volts. Oh, if I got another meter floating around that I can get on camera that works. Simple things turn into complex problems. Do believe the battery in this guy is dead, and it is. And I don't think I have a 9-volt cell floating around here at the moment. Okay. We'll take this guy out of circuit. we've kind of seen, oh, maybe that's why it wasn't measuring anything. There it is. Okay. We're seeing the voltage now across the filter cap, just because I find that kind of interesting. Now let's see if I can get volts DC. Oh, that's what I was doing wrong. That's exactly what I was doing wrong. I was thinking I needed to measure current here, and I actually needed to measure voltage, where 1 microvolt or 1 millivolt equals 1 milliamp. So we'll just substitute this around. We're on volts DC. Current draw currently is down under, so we're at 1 millivolt, so the current draw is very little. Let's get it up out of current compliance. Bring the current up. So the dancing I'm seeing on the meter movement is real. And it looks like I can't get steady regulation until about 500 milliamps. So what we're seeing here is I got about 500 milliamps draw into the load, and the current draws become consistent, and the power supply is still set to 10 volts. And as I bring the current down, it's 400 milliamps. See if I can get this to freak out again. 320 milliamps. 280, 260. Still rock solid 10 volts. And there it goes. It's, oh, maybe not, 119 milliamps. Let's keep bringing the load resistance up. And now we're kind of getting into this weird range where the meter movement's wiggling. The voltage looks rock solid. The output voltage at 10.003 volts. The current has settled at 40 milliamps. Okay, I'm going to take the output voltage up to the full 20 volt rail. So we're, see if I can get it spot on 20. It's a little touchy. There's 20.004 volts output on the supply. I believe I've got the current compliance up as high as it'll go. And let's bring the load up. So we're decreasing the resistance. Loading on the power supply, we're in that weird region again where I just can't get things steady. I don't know why that is. It could be an issue with regulation in the supply, although the voltage is rock solid. You know, maybe I'm under the minimum point where the electronic load is stable. I just don't know. But I'm going to keep bringing the current up. See if we can get up towards an amp. Oh, this pot is just so cheap. So I'm in the range on the meter movement of 800 milliamps. The voltage output is still at 20.007 volts. You can see that the voltage across the filter cap here is dropped by 5 volts because of the current draw. So remember, we're taking AC through a diode bridge someplace to pulsating DC. So we've got our sine wave. Hopefully this will make some sense with our DC down the middle. Do I have a piece of paper I can draw on? And something to draw with. And something to draw against. And I'll try to draw out kind of what's going on here. And maybe do a little bit of education as best as I can do it. We've got, of course, AC voltage at 60 hertz coming into the transformer. If we've got ground here, the output side of the transformer is, of course, going to be a sine wave, where this is positive and this is negative and this is ground. I'll call it a 0 volt reference. And what the diode bridge is doing is taking this side of the AC voltage, and it's flipping it so that it lives up here. So this goes away, and the diode bridge has now got us having pulsating DC, and then the filter cap is across this voltage to basically, while the output of the transformer rolls off, to try to hold that voltage steady. And so what happens is, as we increase load, the filter capacitor has to work harder, because during these times when the voltage out of the diode bridge is dipping below, on the filter cap it'll roll off. So on the filter cap, we're potentially going to see under no load a nice DC voltage, and then as it becomes load, we're going to see it roll off, and we get ripple. So, and that's the filter cap's job, is to try to convert this to a smooth DC and deal with that ripple. And the reason you want the voltage across the cap higher than the output capacity of the meter is this ripple lives above. So this ripple is, probably up around in the 30 volt region now, but the supply is trying to output 20 volts. So there's 10 volts of there's 10 additional volts here that can be played with by the regulation. So as this voltage on the filter cap is moving, the regulation could be rock solid, because this is never dipping down below the regulated voltage. Hopefully that made some sense. I'm not the best at explaining these kind of things. There's a million tutorials out on the web that go into this. And we've been drawing 800 milliamps here, 816 actually, at 20 volts for quite a while. I'm going to go ahead and bring this up closer to the 1.2 amp apparent rating based on the meter on the power supply. So there's just over an amp. 1.1. So we're at 1.205 amps. The meter movement isn't particularly linear. You can see the voltage across the filter cap has dropped down to 29.5 volts. The regulated output is now down to actually 19.994 volts. And this is what we talked about earlier. As this current draw gets higher, I'm using really flimsy, cheap wires here. And so what's happening is, although because I'm actually measuring the voltage at this point rather than measuring the voltage out at this point, but yeah, we're getting loss in these leads. There's some kind of voltage drop across these leads, this kind of current, so there's loss in the system. Now the voltage is really rolling off now. Something's getting warm. 17.5. Yeah, I can feel the heatsink warming up. So the power supply's quickly lost regulation. 16.5 volts, 16.3. Yeah, something's warming up and causing issues up at the higher current. Lowering the current slightly to 117 milliamps, or 1.178 amps. Brought the voltage right back up to the 20 volts. Anyhow, part of what we're seeing here is I'm showing 20 volts output here. Let me see if I can get these loose, get these leads removed. And what I want to do is measure the actual working voltage we're ending up with up here. Although I've got the leads backwards, so there's 19.71 volts appearing here, even though there's 20 volts appearing here. This is what I was talking about earlier. So we've ended up with a working voltage of 19.7 here coming up to the load. Yeah, 19.7. So there's 0.3 volt loss. Problem with working on a bench is every lead has to find every other lead and get connected to it. Let me get the voltage monitor on the filter cap hooked back up. So we're still seeing 28 volts there. So I'm seeing 20 volts here and 19.7 volts here. So there's 0.3 volts being lost in the system. And if I measure the voltage across this white lead here, we're measuring 50 millivolts. We'll probably see about the same here. 51 millivolts. So if I take the voltage here, and sorry this isn't on the meter. Now I can't get a good measure here of the output voltage. 20.04. Come on, bite on there. 19.6. So that's losing about, what, 30 or 40 millivolts. We're seeing, the math isn't working here, but we're seeing it says 48 millivolts lost. But what we're seeing is an actual voltage drop across these cheap leads I've got. If we had the sense hooked up, oh yes, you're unhappy. If we have the sense hooked up, we'd have two more leads coming from this power supply tied to these 2 points right here. And the supply would be sensing that voltage drop due to the wiring like I described earlier, and it would drive the output voltage up slightly to make up for it. And it would try to maintain the voltage here as close to 20 volts as it can. And that works because although there's 1.2 amps flowing in these small wires here, the sense is just measuring voltage. There's very, very little current flow in those sense leads. And so there's very little drop across them. So, it's known as a 4-wire power supply. There's Kelvin connections on meters. There are 4-wire that kind of work the same way, where if your ohm meter is measuring resistance, the meter's actually putting out a voltage, and that voltage causes a current flow in the resistor being measured. And knowing what the voltage is and knowing what the current flow is, the meter can calculate the resistance. It's just simple Ohm's law. For very low resistances, if you're dumping a lot of voltage into it, you generate a lot of heat, and you don't want to do that. So for very low resistances, you're putting out a pretty low voltage, but it's into a low resistance, so there's still current flow, and so you're still getting voltage drop across the leads and how you have things interconnected. In a 4-wire Kelvin measurement on a meter, you've got the same thing. You've got 2 sense leads coming out directly to the resistor, and that way the meter can measure the voltage directly across the resistor and get that voltage to what it wants it to be, then measure the current and give you a much more accurate calculation. So it's remote sensing. It's really useful in low current. It's really useful when you want an exact voltage at some point, and the system will make up for lead loss, for loss in various connections and that kind of stuff. So let's see, what's the voltage we've got happening here? So it's still at 20.01 volts. We're drawing 1.179 amps. So I suspect when I saw the voltage starting to roll off earlier, is it's doing there. Or no, it's just me not holding the lead steady. So at 1.2 amps, the output voltage has actually dropped to 1.4 volts. That's interesting. Have we just gone into hard compliance on the supply? What does it think it's outputting? Yeah, that's consistent with the meter movement on the front. So getting up to around the 1.2 amp, the meter does, or the power supply does go into compliance and clamp the output voltage, pulls it down. We're back up at 20.003 volts on the output. So this supply is actually good to 1.15 amps, maybe 1.17, before it just drops into compliance and drops the voltage off due to overcurrent, which is really kind of cool. If I bring the load resistance back up, so I increase the resistance, the current will drop in the system, and you'll see the voltage across the filter cap come back up as we're putting less and less demands on that filter cap to provide current into the system. And we're down now at 249 milliamps. And you can see the filter cap has come back up. Now we're in that weird spot where things start to oscillate. Oh, there it became steady. So I don't know if that oscillation I'm getting at very low currents is this guy just not working well at really low currents. He's really designed for high current loads and dissipation, or the power supply. The goal with this electronic load is to be able to dump lots of power into it. As I said earlier, the load is the MOSFETs that are directly across the incoming power supply. The system is basically, it's varying the resistance, those two MOSFETs that are in parallel. Those MOSFETs are the load with current going through them and resistance. It's E times I for power. From that, you can calculate the heat dissipation in watts, and that energy is being dropped into these old Pentium heat sinks, and then a couple of fans to just keep the system nice and cool. So all this guy really does is convert current into heat and dissipate the heat, but it gives you a way of having a consistent load. So the idea here is I can set the load, I've set it to 165 milliamps, and if I vary the output voltage on the meter, so I'm bringing the voltage down on the meter. Actually, let's go back and approach this a different way. I'm going to stop monitoring the filter cap, and I'm going to see if I can get to the point where I can monitor the actual output voltage of the system. And we'll talk about this electronic load a little bit. The current, of course, just dropped to 0 because I've disconnected. Oh, got a really nice spark there when I reconnected as the current surged. So what we're seeing here is the 20 volt output. Let's just bring the load up a bit to something a little easier to read. Well, maybe a little easier. Oh, well, I'm going to leave it there. Hopefully, doggone it. Another really nice spark as I disconnected the load. Another really nice spark reconnecting the load. Let me get in here so we can measure the voltage. So the output voltage of the power supply is sitting here. The current draw in milliamps is displayed here, 223. As I bring the voltage down on the power supply, so you can see we've dropped to 18.2 volts, but notice the current is steady. This is a constant current load. And that's its job, is no matter what this voltage is within a reasonable range, it maintains a constant current on the load. So there's 16 volts, 15. This load continues to draw 223 milliamps, and that's the idea of the constant current load, is over a range of input voltages, it will draw the same current. If I had a resistor in here like we had earlier, we had the little resistor pack in here, this is just a fixed resistance, and so as I drop the voltage, the current would roll off. The resistance of this unit is changing as needed to maintain that current flow, basically independent of the input voltage. So fixed resistance, this guy becomes a variable resistance with feedback to maintain current. So we're down at 5 volts output, still drawing 223 milliamps, and I would expect the 223 to really be rock solid until, there's 0.61 volts output, 223 milliamps. There will be a spot here, potentially, where this will collapse, or maybe not. There it goes. So again, too many leads. So up at 0.27 volts output, we've got our 223 milliamps, and as I bring the output voltage slowly down, you can see the current starting to draw. So we're getting down into really the low voltage area of the regulator in the supply, where it's starting to lose regulation. It's just kind of, just how things are. Most power supplies can't regulate all the way down to 0 volts. There's going to be some margin where they just can't do decent regulation under and maintain current and voltage and everything, and that's typically got to do with voltage drops across PN junctions and that kind of stuff. Hopefully I'm not lying too much here. Well, this has been a neat little experiment. I hope you've learned something. I hope my description of things has been somewhat accurate and understandable. The words that come out of my mouth aren't always the words that are rotating around in my head as I think about these things. Kind of a neat little exercise. We're kind of abusing the supply with this long lead length here and the dropping it to the filter cap. But still, it has proven itself to be a pretty capable little power supply for what it is. We're back at our 223 milliamps, 20 volts. We'll bring the current up, get it into the 1.1 amp, 500 milliamps, 600 milliamps, 700, 800, 900. We're getting towards the 1.1 amps. We're getting towards the top end of what the power supply can actually deliver. It doesn't get to 1.2 amps with stability, but we're still 20.41 volts on the output. 1.179 amps draw. Of course, these aren't even going to... Oh, that actually is a bit up above ambient. Oops, I touched the fan. Yeah, that might be a bit above ambient. 20 volts, 1.2 amps is again going to be 20 watts. What is that? 24 watts. Something like that's about 24 watts. Not a huge amount of power, but not an insignificant amount of power either. So I will just let this sit and cook for a bit. Hopefully not come back when I come back upstairs from fire, or come back up to fire and smoke and all kinds of horrible nastiness. Hell, this video's rambled on forever. Hopefully there's been something, like I said earlier, educational. I'll end here. I'll probably do another video on the teardown and repair of the supply, since people tend to enjoy watching that. And we'll talk soon.